80 meters. The world saw an impenetrable fortress. Iran's Fordow nuclear facility, buried deep inside a mountain near Qom, was supposed to be invincible. But deep inside an American weapons lab, engineers had already begun reshaping the GBU-57 Massive Ordnance Penetrator. 30,000 pounds, a redesigned nose cone, a delayed action fuse, all calibrated to smash through roughly 60 meters of reinforced concrete, not 80 meters of rock. The fortress had a flaw, and they built a key to fit it. The fortress in question was Fordow, a uranium enrichment plant carved into a mountain range roughly 20 miles northeast of the holy city of Qom. Its location was no accident. Before becoming a nuclear site, the facility belonged to Iran's Revolutionary Guard Corps, who had already hollowed out the mountain for ammunition storage and command bunkers. They understood the terrain. The peak above Fordow rises about 1,900 meters, and the deepest chambers sit under a dome of sedimentary rock and igneous strata at least 80 meters thick. Engineers then lined the entry tunnels with reinforced concrete up to 2.5 meters deep in places. Blast doors were installed at multiple tunnel junctions. The main enrichment halls were placed at the end of angled access drifts to deflect shock waves. Ventilation shafts twist upward through narrow secondary routes, designed to dissipate pressure before it reaches the surface. Above it all, air defense batteries nestle into the mountainside, and the entire complex is ringed with razor wire, watchtowers, and earth berms. Satellite imagery from the mid-2000s showed 2 primary entrance portals carved into a sheer cliff face, each wide enough to drive heavy machinery inside. Once within, centrifuges in cascading arrays spin uranium hexafluoride gas at supersonic speeds, enriching uranium to levels just short of weapons grade. The layout itself is defensive: multiple levels, redundant power lines, independent water cooling circuits, and an internal air supply capable of running for weeks if the outside world burns. Iranian generals claimed the facility could survive direct hits from multiple 2,000-pound penetrators. And they were right, at least against conventional bunker busters. But Fordow's deep anatomy had a single vulnerability. Its vertical depth profile meant a precisely timed, deeply burrowing weapon could fracture the rock cap from below, collapsing the protective shell inward. The target was buried, but not beyond reach. For decades, the standard solution for hardened targets was the GBU-28. Developed in 1991, this 5,000-pound laser-guided bomb used a forged artillery tube as its casing. It could pierce roughly 100 feet of earth or 20 feet of reinforced concrete. But those numbers meant nothing against a mountain. Penetration physics is unforgiving. A bomb's burrowing depth depends on mass, casing strength, and impact velocity. The kinetic energy on impact must be focused into a narrow cross-section to push through rock. Yet granite, the shield around Fordow, can withstand compressive forces exceeding 20,000 pounds per square inch. When a bomb hits at near-sonic speeds, the stone resists with equal ferocity. The casing must survive colossal deceleration without deforming or snapping. The GBU-28's steel body and internal explosive fill imposed hard limits. If it struck granite at typical drop speeds, the nose would crumple or the entire weapon would shatter before meaningful penetration occurred. Even if it held together, its mass was insufficient. To double penetration depth requires roughly 8 times the mass, not twice. There was a ceiling. The bomb would either ricochet, break apart, or detonate too shallow, leaving the facility intact underneath. Thus, Fordow's mountain demanded a fundamental redesign, a weapon that could not just punch deeper, but survive the impact long enough to deliver its payload from inside the rock. The answer came from Boeing's Phantom Works. They called it the GBU-57 Massive Ordnance Penetrator, or MOP. It is not a conventional bomb. This is a 30,000-pound monster, stretching over 20 feet long. To put that weight in perspective, a fully loaded city bus weighs roughly the same. It uses GPS guidance with inertial backup, steering itself onto precise coordinates. But the real innovation hides in its skin. The casing is forged from a thick nickel-cobalt steel alloy. This metal is chosen for one brutal reason. It must survive a collision at supersonic speeds with solid granite. The structure is dense, streamlined, and exceptionally hard. Inside that armored shell sits a 5,300-pound high-explosive warhead. The delay fuse allows the bomb to burrow deep before detonating. Boeing developed the MOP under an urgent Air Force contract. The threat driving every engineering decision was clear: Iran's deepest, most fortified sites. Fordow's Mountain had rewritten the rules, and this weapon was the calculated response. In most cases, bunker busters hit their target, then detonate inside. This one had to keep going, drilling through tens of meters of reinforced concrete and stone. Its sheer kinetic energy on impact is staggering. The MOP was designed specifically to crack open targets previously considered untouchable. But delivering such a weapon requires an aircraft equally extraordinary. Only one platform in the American arsenal can carry the Massive Ordnance Penetrator into hostile territory, the B-2 Spirit stealth bomber. The B-2's flying wing design and radar-absorbent skin allow it to slip through dense air defenses that would shred conventional bombers. Its internal weapons bays hold 2 MOPs, each weighing nearly 15 tons. No external pylons, no added radar signature. The bombs sit flush inside the jet's belly, completely hidden until the bay doors snap open. These missions originate from Whiteman Air Force Base in Missouri. From there, a B-2 crew flies a non-stop round trip of roughly 25 hours. Crossing the Atlantic, refueling multiple times over international waters and Allied airspace, the bomber arcs toward the Middle East under strict radio silence. The pilots rely on mid-air refueling from tankers like the KC-135 or KC-46, taking on fuel in complete darkness to avoid visual detection. The approach to a target like Fordow is meticulously planned. The B-2 descends to low altitude only at the final attack run, using terrain masking and jamming support to confuse Iranian radar. By the time air defense operators realize something is wrong, the weapons are already away. The bomber then climbs and turns back toward home, its crew facing another 12 hours of tense, fatiguing flight before they land again in Missouri. No other aircraft can combine this range, payload, and invisibility. The B-2 and the MOP are a marriage of necessity, built for a single brutal purpose. That purpose unfolds in a split second when the MOP releases from the B-2. Gravity and its own mass take over. It stabilizes with grid fins, then accelerates. Terminal velocity is supersonic, roughly Mach 1.2, over 1,400 feet per second. The bomb's thick casing, forged from a single piece of high-strength steel, is designed to survive this impact. At contact, the force exceeds roughly 100 million foot-pounds. The blunt nose cap prevents deflection, channeling all that kinetic energy straight down. The first layer might be soil, then rock, then reinforced concrete. The bomb does not explode on contact. A delayed action fuse, hardened against immense shock, waits. Accelerometers inside count the milliseconds and the layers, detecting voids and floors. Only when the weapon has pierced its predetermined depth does the fuse arm. The MOP can bore through up to 60 meters of reinforced concrete, equivalent to a 20-story building buried underground, and even deeper through layered granite like the mountain above Fordow. As it tunnels, its body remains intact, shielding the 5,300-pound explosive payload. The warhead, a blend of AFX 757 insensitive explosive, stays stable. Then, deep inside the buried halls, the fuse triggers. The explosion creates a massive overpressure void, instantly collapsing fortified chambers and tunnels. The mountain itself becomes a tomb, crushing centrifuges, personnel, and equipment with no escape. There is no secondary blast, no fireball visible outside. Just a silent, seismic shudder as a nuclear facility vanishes from the inside out. But getting to that silent shudder took years of frantic engineering. After the MOP's initial fielding in 2011, intelligence flagged a disturbing trend. At Fordow, Iran was thickening concrete casings, adding rubble traps and driving chambers deeper into the mountain. The original MOP risked blunting itself against extra-hard granite and newly reinforced vaults, so the upgrade race ignited. Engineers first tackled the fuse. Early models sometimes detonated too early, or not at all, when striking multi-layered geology. The Air Force refined a smart fuse at White Sands Missile Range, running multiple drop tests from B-2s on target arrays of high-strength concrete and rock. The new sensor package could count empty spaces and void layers, triggering only after penetrating the final intact shell, crucial for Fordow's nested chambers. Next came the explosive fill, Chemists adjusted the AFX-757 composite to achieve a slightly slower but deeper shockwave, better matched to the mountain's geology. The explosive weight stayed around 5,300 pounds, but its burn characteristics shifted. The goal: collapse caverns from within rather than just breach them. Guidance refinements followed. MOP received GPS anti-jam upgrades and a more agile tail actuator. This let bombers release from higher altitudes or steeper off-axis angles, improving accuracy on the precise ventilation portal coordinates at Fordow. On multiple test drops in New Mexico, inert weapons struck within 2 meters of aim points, even in dense electronic warfare simulations. Each iteration taught the weapon to read the mountain like a code, and then erase it. But understanding the mountain's internal structure was only half the equation. The weapon needed a script, a precise three-dimensional map of what lay sealed inside Fordow. Without it, the Massive Ordnance Penetrator was a blind hammer. Fordow's uranium enrichment plant sits roughly 80 to 90 meters beneath a mountain dome near Qom, a hardened complex originally designed to survive a direct nuclear strike. Its tunnel network stretches roughly a kilometer, branching into multiple centrifuge halls, auxiliary chambers, and deep vertical ventilation shafts. Those shafts aren't just air ducts, they're potential pathways for blast waves and fragmentation, making them critical aim points. Assembling that target package took over a decade of intelligence fusion. Mossad operatives provided physical dimensions smuggled out of the facility. CIA analysts cross-referenced those with satellite imagery, tracking construction changes year by year. Ground-penetrating radar signatures from airborne platforms mapped the mountain's internal density anomalies. Even the 2018 Mossad seizure of Iran's nuclear archive in Tehran yielded engineering diagrams that revealed exact hall dimensions and tunnel trajectories. Seismic sensors placed in the region measured ambient vibrations, pinpointing machinery locations. Some reports suggest that features like ventilation intakes, emergency exits, and geological layers were mapped, though full details remain classified. The fusion built a digital twin of Fordow's insides, depth of the main centrifuge hall, roughly 15 meters of reinforced concrete plus 60 meters of solid rock, location of the cascade piping, thickness of blast doors. In many cases, a bunker buster's fuse and penetration parameters are informed by a target model, but specific details for the MOP are not publicly confirmed. In some accounts, a gap in intelligence could cause a bunker buster to detonate at the wrong depth, possibly before reaching the target. The effectiveness of such a weapon largely depends on the accuracy of the intelligence behind its targeting. The mission begins before dawn. Electronic warfare aircraft surge forward, jamming air defense radars across western Iran. F-35 stealth fighters follow, releasing decoys and hunting mobile SAM launchers. Their job is to blind the defenders and carve a corridor through the sky. 200 miles from the target, a B-2 Spirit bomber, invisible to radar, crosses the Iranian border at high altitude. Its payload bay holds 2 GBU-57 bombs, each weighing 15 tons. The bomber flies a precise route, using terrain masking and cloud cover to avoid detection. As it nears the mountain near Qom, the B-2's bomb bay doors open. The first MOP is released from roughly 40,000 feet. It accelerates, fins guiding it to a near vertical angle. The weapon strikes a single entry point on the mountain slope, a shaft entrance to the Fordow facility. The bomb's hardened steel casing drives through rock and concrete, its fuse counting floors. It detonates deep inside, in a chamber roughly 80 meters below the surface. Minutes later, a second MOP falls along the same trajectory. It impacts the same crater, penetrating deeper into the already fractured rock. The shockwave tunnels through the interconnected chambers. Ceilings buckle, support pillars shatter. A cascading collapse follows, crushing the centrifuges and sealing the facility in a tomb of broken stone. The B-2 might turn away, its mission complete, leaving only a plume of dust rising from the mountain. But Fordow was never meant to be an easy target. Iran layered a formidable defensive ring around the mountain. Russian-made S-300 and S-400 air defense batteries, layered with point defense Tor M1 systems, created a protective dome over Fordow. But the true nightmare scenario may never have been about whether the bomb could penetrate the mountain. It was about what happens after. A direct hit on the centrifuge halls by a massive ordnance penetrator would not trigger a nuclear explosion. The weapon carries no fissile material, yet the consequences could still be radiological. Inside Fordow, thousands of interlinked centrifuge cascades spin at supersonic speeds, processing uranium hexafluoride gas. This compound is highly volatile, corrosive, and toxic. When the MOP detonates, its 5,300 pounds of high explosives would instantly vaporize the centrifuge arrays, shattering the gas cylinders and feed lines. The resulting fireball would aerosolize roughly several hundred kilograms of uranium hexafluoride into a superheated plume. The blast wave would then propel this toxic cloud out through the entry tunnel and ventilation shafts, venting directly into the arid air above the mountain. As the gas cools, it reacts violently with atmospheric moisture, breaking down into hydrogen fluoride gas and fine particulate uranium oxide. Prevailing winds, typically from the west-northwest, would carry this invisible hazard across Highway 7 and toward the outskirts of Qom, a city of over 1.2 million people, located less than 30 kilometers away. The resulting contamination zone would not be a nuclear wasteland, but a chemical and heavy metal hazard. Inhalation of uranium particles poses long-term kidney and lung damage risks. The hydrogen fluoride cloud, even diluted, can cause severe respiratory burns. Decontaminating the mountain site itself would be a generational undertaking, rendering the area a quarantine dead zone for decades, a poisoned monument buried in the rock. But the weapon's true power extends beyond the blast crater. The mere existence of the Massive Ordnance Penetrator rewrites the strategic equation. Fordow, once hailed as a sanctuary buried under 80 meters of mountain rock, is now revealed as vulnerable. Iranian planners, who spent over a decade reinforcing the facility with reinforced concrete and steel inner chambers, must now accept that no depth guarantees safety. The certainty of an impregnable Fordow created diplomatic leverage, a nuclear hedge beyond the reach of any conventional strike. That certainty is shattered. The weapon's demonstrated penetration capability, roughly 60 meters of reinforced concrete, forces Tehran into a painful calculus. They can attempt to dig even deeper, perhaps 150 meters or more, but that requires years of additional construction, massive expense, and geological limitations near the ancient Qanat water channels of the region. Alternatively, they can pursue deception, dispersing centrifuges to multiple hidden sites, burying decoy facilities, or hardening underground with electromagnetic shielding against the bomb's hardened target fuse. But every deception increases complexity, risk of detection, and overall cost. The third path is diplomatic hedging, accepting stricter inspections or limiting enrichment levels to avoid a strike, knowing the MOP makes that strike far more plausible. Each choice carries a price. The bomb does not need to be dropped to influence Tehran's behavior. Its symbolic weight alone tips the balance, making Fordow a liability rather than an asset. The once impregnable mountain now stands as a potential tomb, its strategic value undermined by a weapon that exists for one purpose: to obliterate deeply buried ambition. This is strategic signaling of the highest order, the threat more powerful than the detonation. And yet, even a weapon this immense confronts hard physical facts. The MOP can certainly collapse the centrifuge halls buried inside Fordow, crushing the delicate rotor assemblies beyond repair. Access tunnels that snake through the mountain would likely cave in, sealing the facility. But the real objective, permanent denial of Iran's enriched uranium stockpile, remains uncertain. Uranium hexafluoride gas stored in cylinders might survive in scattered pockets, shielded by debris. Solid uranium metal or oxide powder, packed in robust containers, could endure the shockwave and fire. Recovery teams could potentially salvage kilograms of material from the rubble, given months of excavation. Then comes the intelligence blind spot. After a strike, satellite imagery can confirm cratering and entrance collapse, but it cannot peer through hundreds of feet of rock. Seismic sensors might register secondary explosions or cave-ins, yet they cannot distinguish between destroyed centrifuges and intact uranium caches. The only way to verify total destruction is to put inspectors or special forces on the ground, deep inside the mountain. That requires a follow-on operation far more dangerous than the bombing itself. Without boots on the ground, the bomb's full success remains a guess. So the MOP offers a powerful but incomplete answer. It can break the mountain's back, but it cannot guarantee the nuclear genie is entirely back in the bottle. That sobering gap defines the weapon's ultimate limit.